Thank you very much, Olivier, and thanks the organizers, Michael and Johannes, for putting this nice workshop together. And thank you for attending. So I'd like to tell you about some recent experiments in our group working with ions and atoms. And what you see here is an overlapped image of a single strontium plus ions immersed in a cloud of ultra-cold rubidium atoms. Before I start with the physics, I'd like to acknowledge and thank all the heroes who actually did this work. We started working on this experiment, I believe, in 2010, so it already has 3 generations of graduate students who graduated from this experiment, and their names are here. And this is really, I don't know if it comes out from the talks that people give here. It's one of the hardest experiments, at least I worked on, so they deserve all the credit for it. Right, so as many people here have already described, the interaction between ions and neutral atoms at long range scales as -1 over to the r to the 4th, or the electric field of the ion squared. And with that type of potential, at least classically, we can think of 2 types of collisions that happened farther than the impact parameter, the critical impact parameter BC, which only cause slight glancing collisions and don't impart much momentum or momentum transfer between the atom and an ion, and collisions that happen at a shorter range than that impact parameter, which then turn into Langevin type collisions. The atom and atom spiraled inwards and collide at close contact. And Langevin collisions are responsible both for the efficient momentum transfer between these 2 species, but also for all the inelastic rates. All the chemistry happens only due to Langevin collisions, and the Langevin rate is an upper limit to the rates at which chemistry or any inelastic processes can occur. As was also mentioned before, the Langevin rate, at least classically, the cross-section goes like 1 over the square root of energy, and therefore the rate, which is proportional to the cross-section times the velocity, is completely independent of energy. Now, how do we connect this classical rate or classical cross-section to quantum calculations? Well, the semi-classical approach would say that the Langevin cross-section is equal to a prefactor times a sum over all partial waves that are involved up to the maximum partial wave my energy allows for, 2L plus 1 times sine square of the phase that the wave function in the relative frame acquires during the collision. Now, if I have many partial waves, I can average this sine square term into 1/2, and then I retrieve the classical Langevin cross-section. If I want to depart from this classical regime of multiple partial waves, I need to cool my system down to energies in which only 1 partial wave is allowed, to the S-wave regime, and also as discussed here previously, due to the softness of this -1 over r to the 4th potential, r star, or the typical, if you like, the distance of the centrifugal barrier of the P wave from the origin, is very large. It's on the order of hundreds of nanometers. For strontium plus rubidium, this is 265 nanometers, which results in an energy barrier to be below in order to get the S-wave regime, which is extremely low, about 80 nanokelvin or so. And as also discussed in this conference previously, the fact that we work under time-dependent fields, the RF of the pole trap, we're limited in the energy that we can achieve. And there are wise choices you can make using a very fat ion and a very light atom. We heard about barium plus lithium and ytterbium plus lithium. We work with rubidium and strontium plus, which have exactly the same mass, depending on the isotope. So this is in many ways the worst choice you could make if your aim is going to the quantum regime. We're limited to temperatures of about 100 microkelvin, in which many partial waves are involved. We actually get some funky physics that I'm not going to describe here, so power law, energy distributions with moments that are dominated by, by extreme events, and the trap plays a significant role, which is something I am going to speak about, but we're limited in the energy that we can achieve. The physics that I'd like to describe here is physics between strontium plus and rubidium, is that of spin dynamics, which is a very useful, it's very interesting physics, and it's also a very useful tool. So here are the results of an experiment where we took our ion and initialized that either, so no nuclear spin, states are either +1/2 or -1/2, and we initialized it in one or the other, and then polarized the rubidium gas either to the stretch state of the lower hyperfine manifold, the F = 1, or to the 0 state where the atoms are not spin oriented. And what we found is that if we align the gas in a preferred direction, we see that spin exchange collisions align the spin of the ion together with that of the gas. It takes about 15 or so collisions for the ion to get polarized. It gets polarized at the 90% level, and it's polarized at the 90% level because spin exchange occurs on average after 9 collisions, or if you like, the probability for a spin exchange collision to occur given a Langevin collision is roughly 10%. But there's also spin relaxation involved. Luckily, it's weaker, and that's why polarization does occur. If we are not orienting our rubidium atoms, then we see that the spin of so if there's no preferred direction, we see that the spin of the ion gets completely mixed to an equal superposition of plus and minus 1/2. Actually, this is a handy tool, and I don't want to dwell a lot on that, but this collision channel of strontium plus rubidium is not the ground state of this molecule. The ground state is, in fact, adiabatically follows to rubidium plus strontium, and that means the charge exchange is radiatively allowed. However, since the ground state of strontium rubidium plus is a singlet state, radiation can only take you from the singlet state to the ground state, and we indeed see that when we polarize our atom and ion, we overlap the triplet much more than we overlap the singlet, and this way can control, by aligning the spin of the cloud, we can control the rate at which charge exchange occurs. So how do I think, in terms of this semi-classical or quantum description of spin exchange collisions, how do I think of spin exchange? And one way to think of it is up-down becomes down-up. I can write both of those as an odd or even superposition of the singlet and triplet states. And then if a collision occurs and I have an interferometer that splits the wave function over the singlet and triplet, the phase acquired between these two would lead to spin exchange, right? So how do I calculate the cross-section of spin exchange collisions? And this is a semi-classical model due to Delgarno from the 1960s. Again, I have this prefactor and sum over all partial waves with a sign, and that sign, though, is not the phase acquired during the collision of the wave function, but rather the phase difference between colliding on the singlet and the triplet. And I have an additional prefactor, which is simply the matrix element of the spin coupling operator between my initial and final state. Semi-classically, again, this sign function would be 1/2, so there's no phase sensitivity. And this prefactor actually turns out to be 10%, which is almost exactly what we measured, which is a nice surprise because in order to calibrate the Langevin rate, I'm saying that in parentheses, we had to evaluate the density of the atoms, and we do that with absorption imaging, which is notoriously semi-accurate. So we were very happy that without aiming there, we got a reasonable result. Together with colleagues Timur Tserbul and Masato Morita from the University of Reno in Nevada, we went beyond the semi-classical approximation and calculated what would be expected from that rate using coupled channel calculation, or I should say they calculated and we spoke with them about their calculation. But we don't know a priori the phase difference between the singlet and the triplet. And when we moved the energy gap between the singlet and the triplet, we saw the cross-section follows a beautiful sine function with 100% contrast, which was a huge surprise. It was a huge surprise because we don't expect the partial wave colliding on these channels to be the same the phase to be the same for all partial wave. We expect to be very far away from the S-wave regime. This is S-wave-like behavior. However, when we looked at on that phase for the different channels, we saw that while the phase, and what you see here is the sine square for the singlet and triplet separately, you see the sine square samples the interval between 0 and 1 almost uniformly. The phase difference between them is fixed, is locked to a given value. And when you change the energy difference between the singlet and the triplet, you get these nice oscillations. The intuition as for why you get that type of S-wave behavior, even though you have multiple partial waves, has to do with separation of length scales. Spin exchange happens at very short distances. Okay, the singlet and the triplet are separate at molecular distances. However, the centrifugal barrier is, as we discussed, hundreds of nanometers away from the origin. And therefore, different centrifugal forces occur at distances much different than where spin exchange physics happens. And that is why the phase difference between singlet and triplet is independent to a large degree of the partial wave which is involved in the collision. It's true until the partial wave is so high that the centrifugal barrier actually eats into molecular distances, and then this type of physics behaves. So if you like, it's a double sword type situation where the long-range physics on the one hand pushes the S-wave behavior to extremely low temperatures, but on the other hand preserves S-wave-like behavior to ridiculously high temperatures. Right, and under this scenario, if you run through the calculation and you vary the energy of the collision, you actually expect to see shape resonances, even with 20 partial waves, which is really a unique feature. Okay, so how would we go about to measuring these things? So the machine we have is a machine in which we trap the ion in the lower chamber, we prepare the atoms in the upper chamber, and then we shuttle the atoms towards the ion with a one-dimensional optical lattice. And by controlling the frequency difference between the lattice beams, we can actually control very well the velocity with which a collision occurs. And also, if we make sure that the atoms are sufficiently dilute, every pass, we know that the probability for a Langevin collision is well below 1, which means that most events we look at are a first collision event before the ion gets a chance of heating up due to multiple collisions in the RF environment. This setup also allows for us to calibrate the Langevin rate accurately and experimentally without needing to evaluate the density of the atoms through absorption imaging. The way we do it is we increase the micromotion, the excess micromotion temperature of the ion, and measure the shelving probability on a narrow optical transition as a function of this energy. Now, for sufficiently high energetic collisions, the ion gets so much energy that shelving with large probability fails. So if you like, asymptotically, this data goes to the probability of undergoing a single Langevin collision. Now, because the Langevin rate is energy independent, by fitting the theoretical curve, and we put in all the parameters of atom-light interactions, we can actually fit and extract the probability of a Langevin collision for the experimental parameters. So the first experiment we wanted to do, we can't really change the difference of energy between the singlet and the triplet and then watch this nice sine function. We have no knob controlling the energy difference between them. But what we can do is measure spin exchange cross-sections over a chain of isotopes. And then, different isotopes would sample the singlet-triplet energy difference semi-randomly. And that hopefully will probe that sine functions at various places. However, in order to perform this measurement, we need all the lasers to work with all the isotopes, and we came up with a different method that we conceptually borrowed from the world of precision spectroscopy, that of quantum logic. In quantum logic, you use a single logic ion and then a spectroscopy ion that you don't control. Okay, all you do is collide the spectroscopy, make sure that photons collide with the spectroscopy ion. The fact that the spectroscopy ion has gone a transition, either internal or external, due to the recoil, momentum transfer from the photon to the ion, is observed through the extreme control of the logic ion. So this method is used in optical atomic clocks, in molecular spectroscopy, in the spectroscopy of highly charged ions. And he borrowed that idea in order to investigate collisions between an uncontrolled ion and its environment, so ultracold atoms. So again, this is our machine. We shuttle a cloud of ultracold rubidium downwards. We trap a pair of ions. One of them is strontium-88, which is the logic ion, the ion we control well. The other one can be anything, really, a chemistry ion. We shuttle the cloud such that less than one Langevin collisions happens on average. And then we measure the momentum that was transferred in the collision through coupling to the logic ion. That momentum can be elastically given. It can also happen through an exothermic inelastic reaction. And in the data I'm going to show you, it was due to a hyperfine release. We initialized the atoms in the F = 2, and every collision that released or transferred the atom from rubidium from F equal 2 to F equal 1 released about 300 millikelvin of energy into that system, and that's easily detectable using the logic ion. So here is data. We measured the cross-section of spin exchange on different isotopes of rubidium using this method, strontium-88, 86, 84, and 87. And what you see, what we found is that all the even isotopes have the same cross-section to within our measurement accuracy, but strontium-87 has a spin exchange probability which is significantly lower. And then what we had to do is find people who can actually calculate and understand this physics, and hooked up with Max, Matthew, and Michal from the University of Warsaw, who calculated the spin exchange probability as a function of the energy difference between the singlet and the triplet. And this is preliminary data, and there's a poster outside if you want to know more. But what they found is that while we don't know where the cross-sections are, all the even isotopes are expected to have the same cross-section, and the odd isotope is supposed to be at the antiphase. So if you like, you have, this is a curve here that shows the dependence of this cross-section on the reduced mass. We have oscillations that are exactly at the rate of 2 atomic masses. So actually, this data is already a preliminary proof of indeed seeing S-wave behavior far outside the S-wave regime, which I find exciting. Another example is a set of data that we took this time with strontium-88 plus and rubidium-87 plus. Again, this technique is very agile, if you like, and you can change your chemistry ion at will. And we looked, instead of spin exchange, we looked at charge exchange reactions. This time it's not radiative charge exchange, it's resonant charge exchange. And we found that the cross-section for resonant charge exchange is significantly, by an order of magnitude, lower than the Langevin rate, which, again, without having a calculation, is a strong indication of quantum interference, of suppression due to quantum interference. Otherwise, you would expect charge exchange to be on par with the Langevin rate if it's a resonant process. Right. So I've shown you that as we change, if you look at inelastic collisions, if you go to different isotopes or choose different species, we can try and detect interference effect. A more direct comparison would be to actually measure this reaction as a function of energy and search for shape resonances. And this is what we've done. We've taken data of spin exchange both for an exothermic channel. Remember that the magnetic susceptibility of rubidium and strontium plus is not the same due to the hyperfine structure of rubidium. So either rubidium starting at 1-1 and strontium starting at up, which is an exothermic spin exchange reaction, or vice versa, which is an endothermic channel. So it either releases energy or costs energy. We measured directly the cross-section as a function of energy. We did not find statistically significant shape resonances. We actually found a behavior which is very consistent with what you would expect from the Langevin cross-section, scaling that goes as 1 over the square root of energy. And the question is why? And there's 2 hints in this data that tells you that the trap plays a significant role in this process. One is that if you look at the endo-exo gap, it actually doesn't close at the Weizmann gap energy, which in this case is about 0.5 millikelvin. It actually closes closer to an energy which would be the gap in the lab frame, and not in the relative motion frame. The other hint is that if I look at the endothermic channel versus the exothermic channel, even though the temperature, the energy of the collision is right around 100 microkelvin, and the Weizmann gap is 0.5 millikelvin, endothermic reaction rates are not fully suppressed. We still see endothermic reactions, and that cannot happen in a single collision. That will only happen if the trap RF has sufficient time to, someone has to pay the electricity bill, right? Someone had to do the work in order for these atom-ion wave function to hop above this Weizmann barrier. And there's only one thing that can do it, the RF fields of the trap. And then we got reminded of the image that you've seen from Marco Cettina's paper, and I'm showing you the results of our simulations. We know that when an atom and ion collide, we actually see very often multiple short-range collisions in this single Langevin event before the atom and ion separate. And in fact, when we run this simulation, we see that this is actually the common case. So we see that happening more than not. And in fact, this behavior has nothing to do with the RF fields of the trap. This behavior has to do with the fact that the ion is trapped, the atoms are free, and if you don't have two free particles, then the relative motion and the center of mass motion are no longer decoupled, and energy and momentum can flow between the relative motion into the center of mass motion. You can see here that when the bound state is formed and the relative motion is oscillating very quickly, the amplitude of the common mode motion, which is the motion of both of them, which is much slower, becomes significant. So in this case, the bond energy was transferred into the oscillation of the molecule in this trap. So the question is whether we can measure this effect. And the first thing we tried was the following. We looked in simulation, what is the average number of short-range collisions that we get in such an event as a function of the micromotion energy, and we saw that if we start with an average number of 5 or 6 or so, after we go to significant micromotion, this number actually does not reduce to 0, but reduces by about a factor of 3. And that means that if we look at the spin exchange probability as a function of micromotion, we expect to see the behavior, and this is exactly what we see. So the ray data here is the exothermic channel results for the probability of spin exchange versus micromotion. The blue data is the endothermic data. And the curves here are the results of a numerical classical simulation that calculates the same thing. By fitting the simulation results to the data, we can actually extract the probability for a single spin exchange reaction given Langevin. Again, we find a value of about 10% in agreement with our previous results and the Delgarno model. By the way, the model for endothermic reactions is actually lower than the data that we measure. The next measurement we did followed the following logic. So again, the ion and atom go into this dance of multiple collisions until they're released. However, if the magnetic field is large enough and the reaction is exothermal, the energy released could be higher than the molecular bond, and that would break the molecule. So what we expect is that under the assumption of multiple collisions and a probability of spin exchange which is small, if the magnetic field is sufficiently high, eventually, when spin exchange occurs, the molecule would break, okay? If the magnetic field is low, spin exchange can happen multiple times before the molecule breaks. In other words, we expect that as we go from a low magnetic field to a high magnetic field, we expect the probability of spin exchange to go up, and this is indeed what we see. The blue data is the endothermic channel, which we expect to get suppressed as we increase the magnetic field. This dashed line here, the solid lines are simply fit to an exponential. The dashed lines are the results of a simulation. The exothermal channel agrees very well. The endothermal channel, actually, we expect to get more suppression that we see again. We did measure the temperature of the atoms that went out, but I'm not going to speak about that just because I'm running out of time. By fitting again to this curve, we could get the binding energy, which is about 0.7 millikelvin. Now, if we look at this is simply a statistical model. We look at the probability for spin exchange, and we look at the ratio between the spin exchange probability at low field versus high field. We can actually extract the average number of collisions that this bound state contains. And by doing so, we measure something like 10 on average collisions, which leads, because we know the potential at long range exactly, we can calculate the period given the bond energy of a back and forth motion, and from that we can extract the lifetime of the molecule, which is about half a microsecond. So to sum up, what I've shown you here is a new technique, if you like, to detect logic, to use quantum logic in order to measure quantitatively atom-ion collisions. Using that method, we're able to observe S-wave dynamics high above the S-wave regime. This is really the result of the long-range character of the potential. Furthermore, we observed trap-assisted formation of atom-ion molecules. And we haven't given up on our hope to measure shape resonances, and we believe that the way to do that is actually work with very weak ion traps like most of my colleagues here do. This is actually a rather tight trap with a secular frequency of about 1 megahertz. I'll end by saying that we do more things than atom-ion mixtures, quantum computing and simulations, metrology, and also together with the Near-Davidson group studying ultracold Bose-Fermi mixtures. I'll thank all the people in the group. And I'll end by showing you Nitzanim Beach, which is 20 minutes away from the Weizmann Institute. And the reason I'm saying that is because we have available PhD and postdoc positions. So if except for doing interesting physics, you also want to spend some time on the beach, then let me know and we can arrange for that. Thank you for your attention.
Thank you, Roee, for your talk. By the way, you should tell also that the temperature nowadays in Israel is quite high. I mean, I've seen that in Haifa, it is like 39 degrees.
Well, that's not part of our sales pitch. We say that in January and February, not in July and August.
Okay, just to say that I've seen that in the O News channel yesterday. Yeah, is there any question about the talk? Yes, René? Oh, yeah, that's microphone stuff.
With these kind of, well, I still don't know how to call them, but kind of the collisions where the atom sticks to the ion because of the trap. You said that you see it basically in the majority of cases. And at some point you said this when you were simulating, I mean, right? That it basically always sticks.
Not always, but what I meant is that if you look at the area under n equal 2 or more and compare that to the case of n equal 1,
okay,
it happens more often.
Yeah, because we were simulating kind of that we see it in half of the cases, which made sense to us because the Paul trap kind of is in the wrong direction in half of the cases, right? It's kind of anti-trapping.
Our trap is always in the right direction.
Yeah.
No, I don't know. Maybe it has to do with the different mass ratios.
No, I would say it probably has to do with frequency, right? Because you drive at a high frequency, and the lifetime of your kind of complex is I think, like multiple.
I mean, we see that even with a completely fictionary static trap in the simulation. You don't need any
okay, but the static trap is always in the right direction, right? I mean, it's not changing.
I see what you mean. And I'm not sure. I'm not sure that argument holds. We can discuss it in detail, and it has to do with the fact that, if you mentioned, and we looked into that as well, that a digital trap doesn't work, and my intuition was let's work with a digital trap because then there's no time-dependent fields, and that never works because somehow the collision dynamics is slower than any conceivable period we could push into that digital frame. So I think the collision, the transfer of momentum between the ultra-cold atoms and ions starts happening at extremely large distances, which translate into very, very long timescales, as compared to the RF. Our RF, by the way, is 26 megahertz. It's not a megahertz.
Right, and ours is 2. So
maybe that's the...
the lifetime of this sticking thing is kind of on the same order. And in your case, I guess it's
longer.
Yeah, exactly.
It's much longer.
So perhaps that's why. But anyway, it was just a thought.
Okay, thank you. Stefan?
So thanks for the great talk, Roee. So related to René's comment, I mean, how strongly does this effect depend on the stiffness of the trap?
So
if you have an extremely weak trap, is this still a problem?
So it happens less in a extremely less in a much weaker trap. That's part of the reasons we want to go into much weaker traps. I don't have much quantitative. I'm sorry. With a spring constant. I mean, if you have an infinitely strong trap, this effect is not going to happen either, right? Because there's only relative motion. There's no center of mass motion. If you have an infinitely weak trap, it's not going to happen. So it only happens kind of in between. Yeah, and apparently we're hitting some sweet spot in that respect.
And second question, if I may. So why is this discrepancy between the exothermic and the endothermic channel? Why does the model fit much better for the exothermic channel?
Our endothermic channel does not fit the simulation results, neither here nor here. You see, the simulation would require the endothermal to be suppressed much more than we find it suppressed at high magnetic fields, 20 Gauss. So here, keep in mind that the gap is about 3 millikelvin, and the temperature is 100 microkelvin. So that's factor 30 between the initial energy of the atom and ion and the gap that they need to climb in order for the endothermic reaction to occur. And we find it happening. It's not just happening. We measure the temperature post-selected on spin exchange reactions, so we know the distribution of energies following that reaction, and it's kind of high. It's in the millikelvin range. So this is the gap energy, about 3.5 millikelvin. But the energy of the endothermic pair that climbs that barrier is by no means cold. It's much higher than, it's an order of magnitude higher than our initial energy. So I'm not sure what it's play here. Something is.
Sadiq, question behind you?
Just to say that we have done these kind of simulations for higher order multipole traps, just to actually figure out what is the effect of the collisional excitations. So we have a comparison with quadrupole, octopole, hexapole, dodecapole. Yeah, we just went mad. Anyway, so point is that yes, indeed, it is strongest for the quadrupole, and it moves away from 4. So what Roee was saying is that the tightness of the trap is definitely a strong factor in the whole business. I mean, this was the original argument for why people started considering the higher order multipole traps, right? Because this collisional excitation of the micromotion would suppress. So this actually comes through.
Other questions or comments right now? Maybe I have a couple of short ones. One is that you were showing that you were able to measure the rate of charge exchange between rubidium and strontium plus. It is a very small rate that you got. I suspect that they 10 to minus 20 or so. I mean, it is never perturbing your experiment, right? It's just like you measured it, but on a routine basis, you just do not take that into account, right?
Yeah, that happens once every 10,000 collisions
Yeah,
or so.
okay,
So at the
yeah.
10 to the minus 4, that's the probability per Langevin.
Okay.
So if we measure, if you work at a rate of 1 collision per pass,
Yeah, okay.
passes happen at few hertz. It happens, but it's relatively rare.
And the other thing, maybe I not get it properly. I mean, you observed some suppression of the rubidium plus resonance charge exchange. Do you know why it is suppressed? I mean, because you say, hey, you have destructive interference, but it's just like a guess. I mean,
we don't have the theory. I mean, all we have is the intuition that elastic collisions and charge exchange collisions cannot be differentiated.
Yeah.
Really.
Yeah,
and,
sure. Yeah.
In this case, we would expect the elastic collision rate and the charge exchange rate to be on par. But you're absolutely right. We need the theory to look into this and say whether that's a coherent suppression or not. So I would call this a initial indication, but not a proof by no means.
Yeah, Johannes.
Yeah, so at the end, you talked about the half microsecond lifetime. Yeah? So this goes along, of course, with this whole discussion of what's happening. But still, do you have a simple way, perhaps, of explaining how this order of magnitude of this lifetime of about a microsecond comes about? So what are the relative quantities that we have to kind of look at to get something like this? I don't know, what are the typical collision times within this molecule, and how many collisions can it survive? And is also the trap frequency, how is that involved? I don't know. Would be interesting to have a rule of thumb or some scaling law, perhaps, that one can derive.
I agree. I don't have any quantitative study of that. What I can say is that for our trap parameters, the number of collisions that occur is on the order of 5 to 10, perhaps. So something along these lines. You see here 2 typical examples. It's a few collisions. We see that for fictitious static traps, these bound states survive for much, much longer. So clearly the presence of RF fields and transfer of energy from the time-varying fields into the motion of the atom and ion helps breaking this bound state sooner. And we do see that when we go to weaker traps, the number of collisions becomes smaller and smaller. So the likelihood of getting a single short-range collision becomes significantly higher. These are the three observations that I can say we have from the simulations, but I can't give any scaling laws yet, at least.
Maybe a last question?
Yes, I think it's like following what you're just saying. Like I was wondering if this extra number of collisions, endothermic collisions that you were not expecting could arise from secondary collisions that we get like during these long events in which there are many exchanges and these particles they remain close by. There's another particle arriving and paying the energy bill, as you said.
No, clearly that's a mechanism, but we do take it into account in our simulations. So it would still not explain why in the simulation we run, we get much more suppression than we expect. So we're not taking something into account. But clearly, without having multiple collisions, endothermal reactions would not be able to occur.
Sure. Okay.
Okay, thank you. If there is no other questions, I think we can at least close that session, single talk session, right? So thank you again, Roee. And